At densities of about 10 to the 10 grams per cubic centimeter, protons and electrons combine into neutrons. Now, one of the main consequences of this is that you are getting rid of the electrons. And remember, this is a degenerate core. It's the electrons that are giving you the pressure. What's going to happen is the collapse of the iron core, and you have a neutron star. The collapse is going to happen until neutron degeneracy kicks in to provide support against gravity. Let's see how that works. Now consider the following reactions. You have a neutron that decays into a proton plus an electron plus an anti-neutrino. And a proton and an electron combining into a neutron and a neutrino. So the first one is called beta decay. Beta because it emits an electron, a beta particle. And this is spontaneous. It's the decay of a free neutron. A free neutron is unstable. It's a reaction that is mediated by the weak force. It occurs within a lifetime of about 13 minutes. The second reaction is called the neutronization. And for this to occur, energy must be given because the rest energy of the neutron exceeds the combined rest energy of the electron and the proton. So where does this energy come from? You have on the right-hand side the energy, the rest energy of the neutron. And on the left-hand side, you have the rest energy of the proton and the rest energy of the electron. The energy of the neutron is bigger than the combined rest energy of the proton and the electron. What is needed here is the kinetic energy of the electron, and that's going to flip the energy balance and make this bigger than the energy of the neutron and allow the reaction to happen. This kinetic energy of the electron is the Fermi energy, is the energy of a degenerate electron. The energy of the electron is the Fermi energy minus its rest mass. So this kinetic energy must exceed the mass deficit of the reaction. That is, that the condition for the reaction to occur is that the energy is bigger than the mass of the neutron minus the mass of the proton plus the mass of the electron, and all of this here multiplied by the square of the speed of light. Now, if you write the Fermi energy in terms of the Fermi momentum, this becomes Fermi energy minus the rest mass of the electron must be bigger than this. Now you can remove the rest mass of the electron on both sides and now write the Fermi energy in terms of the momentum. And now if you square both sides, now you can isolate the Fermi momentum. Remove the extra square of the speed of light on both sides. Extract the electron mass on the right-hand side. Now call the mass difference between the neutron and the proton Q, and take the square root of this expression. Oh, sorry, I was missing an electron mass in here. So you can equate this now the definition of the Fermi momentum. And then if you solve for the density, and then you have a condition in terms of the density. That means that the density must be bigger than a critical density. So this is the critical density for neutronization. You can see all the variables in these equations are constant. So this is a numerical value. The value of this critical density is about 1.2 times 10 to the 7 grams per cubic centimeter. When this density is exceeded, neutronization occurs. Notice also that if the gas is fully degenerate, the beta decay reaction does not occur, which is this reaction here. When the gas is fully degenerate, this reaction does not occur. It's inhibited because there are no free states for the electron to occupy. At a temperature of about 8 billion Kelvin and density of about 10 to the 10 grams per cubic centimeter, which is about 15 solar masses, the electrons that gave the degenerate pressure are captured by the heavy nuclei and protons produced by photo disintegration. The support of the degenerate pressure is gone, and the core collapses in free fall. The electrons are squeezed together into the protons, and all of the mass of the core becomes completely composed of neutrons. What you have in the end is a giant nucleus of about 10 to the 57 neutrons held together by gravity and supported by neutron degeneracy.